We will be discussing rates of reaction, specifically chemical rates of reaction in this PowerPoint lesson. The animal shown here is known as the thorny devil. As a reptile, its body temperature varies with the temperature of its external environment. So as the temperature warms up outside, it warms up. If the temperature outside is cold, it is cold. But what does this have to do with rates of reaction? As outside temperatures drop, so does this animal's internal temperature. That causes a slowdown of chemical reactions in its body which produce energy. When it has less energy, it is sluggish. All because these energy-providing reactions within its body have slowed down as well because of colder temperatures. Temperature is one of several factors that influence the rate at which chemical reactions take place, whether those reactions are inside or outside of the body. We start Chapter 6 by looking at chemical reaction rates. The firefly shown here produces its light by a specific chemical reaction in its abdomen. The more of the enzyme luciferase it has, the greater the rate of the bioluminescent reaction. How quickly or slowly a reaction occurs is studied by chemists. Chemists can also determine how these rates of reaction are affected by different factors, such as concentration, temperature, pressure, surface area, and the presence of a catalyst. By the end of this PowerPoint presentation, you will be able to determine the average rate of reaction and instantaneous rates of reaction for different chemical reactions, and it is much easier than it sounds. In determining reaction rates, we are doing chemical kinetics. That is the study of ways to make chemical reactions go faster or slower. Reaction rate, or rate of reaction, refers to the speed at which a chemical reaction occurs, or the change in the amount of reactants consumed or products formed over a given time interval. Quite simply, this is a change in quantity over a change in time. Depending on what we are studying, this could be the change in concentration over time. That would be in units of moles per liter second, or the change in the number of moles over time in units of moles per second, or the change in volume over time in units of liters per second, etc. We will be looking more often at the change in concentration of a reactant or product over time. This is often in units of moles per liter second. We can calculate reaction rate from data provided or determined experimentally, such as the information shown here. In this table, A is a reactant that is being consumed. You can see that its concentration decreases with time. The square brackets are used to show that we are talking about A in terms of concentration. Using information in this table, we can calculate reaction rate. Since reaction rate is a change in quantity, in this case concentration, divided by a change in time, it is calculated by taking the final concentration of A minus the initial concentration of A and dividing that by the final time minus the initial time. The change in concentration of reactant or product over time is often graphed. From this graph, you can see that the concentration of A decreases over time, while the concentration of B increases. Can you tell which is the reactant and which is the product from this information? A is the reactant because it is being consumed, that is, its concentration is decreasing. B is the product because it is being formed, that is, its concentration is increasing. If asked to calculate the rate of reaction of B, how would you do so? You would use a simple formula shown here, where the change in reaction of the reaction rate is delta B divided by delta T, where delta B equals the final concentration of B minus the initial concentration of B in units of mole per liter, and delta T equals the final time minus the initial time, most often in units of seconds. When we talk about reaction rates, there are two kinds to consider: average and instantaneous. The average rate of reaction is a change in the concentration of reactant, or concentration of product over a given time period. I will explain the slope of the secant line in a moment. The instantaneous rate of reaction is at for a particular point in time. For example, that would be the concentration of a reactant at, let's say, 40 seconds. And I will explain the slope of the tangent line in a moment as well. This graph shows how we can understand the difference between these two kinds of reaction rates. The first triangle on the upper left is an example of how we can determine average rate of reaction. You use two data points on the curve and connect them with a straight line. This is called the secant line. Its slope is equal to the average rate of reaction. If you recall from your math courses, slope equals rise over run. In this case, slope equals change in concentration. That's the delta A in square brackets to the left of that triangle, over change in time. That's the horizontal line of the triangle drawn from t equals 10 seconds to t equals 30 seconds. This is the formula you've already been introduced to in this presentation. Now look at the triangle on the lower the lower right. It is an example of how the instantaneous rate of reaction is determined from a graph. Imagine that the points at 40 seconds and 60 seconds have a slope drawn between them, and the points begin to move closer and closer together. At 50 seconds, they converge, and that line that was originally drawn is now touching the curve at only one point. It is called a tangent line. The slope of the tangent line is equal to rise over run. Again, a change in concentration over a change in time. And it is equal to the instantaneous rate of reaction. So you can see that rates of reaction can be determined from data that is graphed. You will be glad to know that you will not have to calculate instantaneous rates of reaction in this way for this course, but you will be doing some calculations with given data. Let's look at sample problem from pages 358 to 359 of your text, which reads, in a reaction between butyl chloride and water, the concentration of butyl chloride is 2.2 times 10 to the negative 1 moles per liter at the beginning of the reaction. At 4 seconds, the concentration of the butyl chloride is 1.0 times 10 to the minus 1 mole per liter. Calculate the average rate of reaction in terms of butyl chloride over the first 4 seconds of the reaction. And with all our problems, it's good to start with what is given. We know that T initial equals 0 seconds, since we are measuring from the beginning of the reaction, and the final time is 4 seconds. We are also given that the initial concentration of butyl chloride is 2.2 times 10 to the minus 1 mole per liter, and the final concentration is 1.0 times 10 to minus 1 mole per liter. We need to determine the average reaction rate. We use the formula that you have already learned, which is the change in concentration divided by the change in time. We put our numbers in with units, and we solve. Notice that our final answer is negative 3.0 times 10 to the minus 2 moles per liter second. This is because the rate of concentration is decreasing. However, it is usually represented by a positive number. To do so, we multiply the answer by negative 1. Our final answer then is positive 3.0 times 10 to the minus 2 moles per liter second. This can also be called the average rate of consumption because the reactant butyl chloride is consumed to make product. As you can see, these calculations can be very easy. Let's look at another problem that's a little different, but still simple. If you know the rate of reaction of one of your reactants or products, you can calculate the rate of reaction of any other reactant or product, as long as you have a balanced chemical equation. Let's look at sample problem from pages 359 to 360 of your text, which says, dinitrogen pentoxide decomposes to form nitrogen dioxide gas. The balanced chemical equation is given. Nitrogen dioxide is produced at a rate of 5.00 times 10 to the minus 6 moles per liter second. And the question is, what is the rate of decomposition of dinitrogen pentoxide? When you look at the balanced chemical equation, you can see that 4 moles of nitrogen dioxide are produced when 2 moles of dinitrogen pentoxide decompose. Rates of reaction are also affected by these molar ratios in the following way. We can use ratios to solve this kind of problem. The ratio of the rate of reaction to be determined to the rate of the given reaction is equal to the molar ratio of the moles of molecule whose rate is to be determined to the moles of molecule whose rate is given. Specifically for this problem, it is the rate of decomposition of dinitrogen pentoxide to the rate of formation of nitrogen dioxide equals the number of moles of dinitrogen pentoxide to the number of moles of nitrogen dioxide. We can put in our given numbers and rearrange the formula to get the rate of decomposition of dinitrogen pentoxide, which equals now a molar ratio of 2/4, multiplied by the rate of the formation of nitrogen dioxide. The answer is 2.5 times 10 to the minus 6 moles per liter second. We can also calculate reaction rates from experiments in which a gas is measured. Consider the following equation, in which calcium carbonate reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide. Data was collected, and the reaction rate for the formation of carbon dioxide in units of moles per minute was needed to be calculated. From last semester, we learned how to use the ideal gas law. If you remember, the equation is PV equals nRT, where P is pressure in kilopascals, V is volume in liquids, N is number of moles, R is the gas constant of 8.314 kilopascal liters per mole Kelvin, and T is temperature in Kelvin. But we need to solve for number of moles. So we rearrange the equation to get N equals PV divided by RT. And we can use that information then to calculate the rate of reaction by dividing the change in the number of moles by the change in time. You can see how easy it can be to calculate rates of reaction for chemical reactions, particularly those involving concentration changes. Take a look at Table 6.2, page 362 in your textbook to see other methods for measuring rates of chemical reactions. Then read Section 6.1 Review on page 364. And finally, practice some of these problems by doing practice problem number 1 to 3 and 6 on page 360, and section review question numbers 1 to 4, 7, 8, and 12 on page 364.